Hello all, I welcome you all to the 22nd lecture. So the last time we met, we spoke about electron-electron interactions and how it differs from the Fermi gas approximation that we have been seeing throughout in this course. So we ended at one point where we saw that in a weakly interacting Fermi gas, you call them a liquid because the scattering between the electrons, if you turn on electron-electron scattering, then you have a new species of particles which are long-lived, which are called as quasi-particles. One particular extension to that is places where you have very strong electron-electron interactions, which cannot be treated perturbatively. So, one such example where you have strong electron-electron interactions is a superconductor. So today, in this lectures, we will see some basic properties of superconductors, and in the last lecture or in the lecture after this, we will see why you need to have a strong electron-electron interaction to exhibit superconductivity. You have what is called as formation of Cooper pairs, which is required for the formation of superconductivity. Superconductors have many applications. We will first see the properties. I will not derive any property in this lecture. In the next lecture, I will introduce a phenomenological model which can explain most of the properties, and I will point you towards a microscopic model first introduced by Bardeen, Cooper and Sheffield, called as a BCS theory. I will not prove the theory, but I will just give you the consequences or the conclusions of the theory. With that theory, you can actually prove many of the fundamental properties of a superconductor. So with that introduction, let me go to the today's lecture, which is Introduction to Superconductivity. I am taking many aspects of this lecture from these two books, Introduction to Solid State Physics by Kittel and Introduction to Superconductivity by Tinkham. In the Solid State Physics by Kittel, look at the superconductivity chapter, and in the Tinkham, I am mostly dealing with only with the first lecture. Tinkham is a book dedicated for superconductors. It's an extraordinarily good book. The name is a misnomer. It is not for beginners, but the first chapter is a good chapter for us to read. The first observation of superconductors happened somewhere around 1911. So you know that the resistance of any metal will drop as you lower the temperature. There are different reasons for this. We saw both of them. The first one is the phonon populations drop, so the scattering probabilities drop. Second, the area to which, or in the case space, the scattering width also reduces with temperature. So basically, you have much less scattering, giving you a reduction in the resistance, right? So basically, you have this linearly reducing resistance. But what Dr. Kamerlingh Onnes noticed in 1911 is that below a particular temperature called as a transition temperature, there is a discontinuous jump in the resistance. The resistance drops. So here, let's say you have about let's say 1.5. It dropped to about 10 power minus 5. Already here it has low resistance. Now the resistance is even low, right? It drops discontinuously at a temperature called as a transition temperature. This is called as a zero resistance state, or a supercurrent state, or a persistent current state. Why this is called as a persistent current state is that if you have a material or a loop, something of this sort, right, and somehow set a current through this loop. I will soon show you how this can be done. Somehow set a current through this loop, then the current in the loop will not die down. The decay time was measured to at least about 10,000 years. They have measured the current for 1 year and then they saw no change in the current value. And if you measure some very small change, they will say that the decay time is at least greater than 10,000 years, 100,000 years, right? This is the behavior of a superconductor. There are superconductors have been observed in many materials. The first one is obviously mercury. It has been observed in lead. It has been observed in tungsten, tantalum, rhenium, iridium, niobium. Niobium has one of the largest elemental transition temperature of about 9.5. Tantalum at 4, tungsten at 0.012, rhenium at 1.4, iridium at 0.14, titanium at 2.3, indium at 3.4, tin at 3.7, vanadium at 5.37, lanthanum at 6, right? And apart from this, you also have transition temperatures of alloys. We will soon see. You will have niobium nitride, you have niobium tin nitride is an alloy. All of them have different transition temperatures. In addition to the drastic drop or discontinuous drop in resistance, you have also what is called as a Meissner effect. What it means is, I was just checking if the mic is on. What it means is that if you keep a superconductor inside a magnetic field and then cool it down, a superconductor behaves as a perfect diamagnet. What it means is there is no magnetization in the superconducting material. What do we mean by magnetization? That means that the spins line up with the magnetic field, right? If the magnetic field is around that direction, you have your magnetization mu into mu dot b, kind of the magnetization force, and you will have the spins which orient along the magnetic field, right, in any material. In a superconductor is a perfect diamagnet, in the sense you have an equal and opposite magnetization force inside the material, such that the bulk of the material remains non-magnetized. So there is zero magnetic induction inside the bulk of the material. Now that is not just that, it is not just a perfect diamagnet. What it means is, when you cool, let's say that you have a material like this, which is a superconductor, above the transition temperature, you have some magnetic field going through this material, it will have some magnetization. If you cool this material down, if you cool a superconductor down from the transition temperature to a below transition temperature, now the material will expel. Now this is a difference between a perfect conductor and a superconductor. A superconductor is a little bit more than a perfect conductor. We will show soon that in a perfect conductor, there is no change in a magnetic flux. So what it means is del cross E is dou B by dou T, right? If there is no resistance in a material, there is no electric field. So this goes to zero. That means that the magnetic flux cannot change in a material. So you take a perfect, let's say I have a material, if I have a bulk of a material which is a perfect conductor, which cannot sustain any electric potential inside this, and I cool it down inside. When I cool it down below the transition temperature with a magnetic field inside, it will hold on to the magnetic field, but the superconductor will expel that. You have what is called as a Meissner effect, right? And you all must have seen the famous example of a levitating superconductor, right? So you have a magnet here and you have a superconductor here, or it can be other way around. It does not matter which is which, right? Typically what happens is you have the bottom one in a superconducting state. It does not matter. So what happens is, when you have something like this, a magnet on a superconductor, you tend to have, let's say, some sort of a surface currents through this, and the surface currents will give you another magnet here which repels the magnet below, right? So basically you have a north and a south pole forming inside the magnet, which repels the superconductor, which acts as a magnet in this case, right? Because of the surface circulating currents. Why there are surface circulating currents? It's because of the fact that your magnetic field now bends, and a bending magnetic field will induce current, right? Del cross B is I. So you have surface currents in a material. We will show in the next lecture that the surface currents in a superconductor die down exponentially, but those things are, we will see when we get there, right? Whenever you add magnetic impurity to a superconductor, it destroys the superconductivity. Something as small as 1 in 10 power 4 moly atoms destroys the superconductivity. 1 to 10 power 4 iron atoms in moly destroys the superconductivity in molybdenum. 1% in gadolinium will lower the transition temperature from 5.6 gadolinium from 5.6 to 0.6 Kelvin. So there is a strong effect of magnetic material inside a superconductor. The Meissner effect, so basically Meissner effect tells you that it will repel the magnetic field, right? And something, so when you have something which is repelling, it is obviously doing some work, right? So it can only repel some strength of a magnetic field. So if you keep on imposing large amount of magnetic field strength, obviously you will break down the superconductivity, right? So that breakdown of the superconductivity at some magnetic field is called as a magnetic critical field, HC. There exists a critical magnetic field that a superconductor can expel. So typically, even there is a magnetic field, the energy in the field is h square by 8 pi, and this h square by 8 pi should be equal to the free energy, Helmholtz free energy of the normal state minus free energy of the superconducting state. Of course, the superconducting state must have lower free energy than the normal state, right? That's why you form a superconductor in the first place. So the difference in the energy should be equivalent to the critical energy in the critical field, right? So any field larger than the critical field will make the material to have an energy larger than the normal state. So it will turn back from the superconducting state to the normal material state. And this HC, the critical current, depends upon the temperature, and it depends for different materials in a different way. So this is lead, mercury, tin, indium. All of them seem to have a kind of a dependence with temperature, which is given by this expression. The critical field has this kind of a behavior. And as we saw previously, if I take a material, the magnetization which exposes or which repels, right? So as I keep applying the magnetic field, you increasingly have negative magnetization in the material, right? Because it is this negative magnetization which repels the field, correct? So it keeps on increasing, and at a field H is equal to Hc, it will drop down, and now it becomes a normal state here. This is a super state. Why this is a negative value? Let's say if it is not a superconductor, this magnetic field will cause some magnetization m, right? And it will cause 4 pi m, and this m is a function of the applied field. Now it is a negative value because the magnetization in a superconductor is equal and opposite to this value. If you add these two together, you have internally zero magnetic field, right? This is the reason why the magnetization in a superconductor is given in negative values. Inside it has anyway have to be only 0, right? So this is any superconductor which displays this kind of a sharp transition in the magnetization at the critical field at some magnetic field is called as a soft superconductor. Most elemental superconductors like lead, mercury, tin, indium have this kind of a behavior. You have some superconductors which are called as hard superconductors. Typically they turn out to be alloys, they typically turn out to be ceramics like yttrium, barium, copper oxide. You have niobium tin nitride, and all these materials, they have what is called as a type 2 superconductor because the magnetization do not have the sharp transition as we saw previously for the soft case. The dashed line is for a soft superconductor. The hard superconductor has one change in the magnetization at fields much smaller than the critical fields of a soft superconductor, and from here it does not go down to 0 immediately but goes down very slowly. This Hc2 for a, let's say for a hard type superconductor can be several Teslas. Remember, Tesla is a huge magnetic field, while Hc1 turns out to be, let's say, less than a Tesla, and Hc2 can be like 50 Teslas. So you will have materials which can sustain huge magnetic fields without breaking down. Now what happens between these two states, between Hc1 and Hc2, you have what is called as a vortex state or a mixed state. So what happens that you have magnetic flux penetrating inside the material at some points. These black dots you see here are regions in which the magnetic flux has penetrated. So let's say I have a superconductor like this. What we saw previously, if I apply a magnetic field, the soft superconductors will have the magnetic field bend around this, right? It cannot penetrate. But when you have a hard superconductor in the mixed state, you will have some regions in which the magnetic flux penetrates. So these are the magnetic flux lines, right? These black dots, and these black dots are seen here. This is called as a mixed state. As you increase the field in the mixed state, these dots get more and more in number, and obviously at magnetic field greater than the critical magnetic field, you have the magnetic flux completely penetrating throughout the material, and you lost the superconductivity, right? In addition to this, there is a very interesting property which is called as flux threading and quantization. This is something which is useful in many applications. Let's consider a ring of a superconductor. As we see here, it encloses an area A, and it is in a magnetic field B. And what is the flux density inside this loop? If this is A, flux turns out to be B into A, right? It is because this is normal to the area here, it is B dot ds integral over this area, which will turn out to be B naught into A, right? And let's say this is above the superconducting transition temperature, and without changing anything, I just lower the temperature. I have not changed the flux, right? As I lower the temperature, this became a superconductor. So now there is no resistance here, right? Now I change the magnetic field B from B naught to B naught plus del B, right? So I have changed the magnetic field, and when I change the magnetic field, obviously there will be an induction, and by Faraday's law, and there will be an EMF introduced into this, and the induced EMF turns out to be minus A into dB by dt. This is the Faraday's law, right? And according to the Lenz's law, if there is an EMF, what is the current, what is the potential in this line? It is L into di by dt, right? This is the current which starts to thread inside the superconductor if you change the magnetic field. Of course, if it is a normal material, you also should have I into R. Because it's a superconductor, this turns out to be 0. So the EMF in this loop, it is L into di by dt, right? So this equation is true if you have a superconductor. Now let us integrate this equation. You will get L into I plus B into A, right, is equal to some constant. So the total flux in this loop will always be constant. So what it means is, how much ever I change the magnetic field, the current in the superconducting loop will change itself such that the magnetic flux inside this loop is always a constant. This is the important property of a superconductor. So what it means is, in this equation, if I change this B being the magnetic field that is applied, if I change this B, the current in this loop will automatically change such that this equation is always honored, right? So this equation always tells you anyway that the magnetic flux density in this loop is always constant. And this particular thing is used in high magnetic fields, very high strength magnetic fields. You must have heard about superconducting magnets and such, right? Which is used in MRI, NMR, all these things. All these things use this principle such that the magnetic flux threading inside a superconducting loop is always a constant. So irrespective of any changes in the magnetic field that you apply, let's say the current that you have, it will always maintain the same flux. Another important aspect of this is that the flux threading the loop. So this is a loop, this is the loop of a superconductor, and the flux inside this loop will always have discrete values. I will prove in the next lecture why it should have discrete values, and it is always shown to have discrete values, and it is quantized by what is called as a flux quantum, which is h cross by 2e. This is a truly quantum mechanical phenomena. Till now we can explain everything of a superconductor using classical electromagnetics, but to show that you have flux quantum, or you have the flux threading inside a superconducting loop to have only discrete values, to have only quantum jumps, which is experimentally observed as shown here by Fairbank, you need to invoke quantum mechanics here, right? So this is another important property of a superconductor. So till now we have seen that you will have discontinuous transition in the resistance. We saw that you have superconductivity is a perfect diamagnet. We showed that the flux threading inside a superconducting loop is always maintained to be constant, and we showed that the flux is can only take discrete values. Another important aspect is the specific heat. Remember, I'm just going through all these properties because these properties were experimentally measured before a theory was proposed. This is the beauty of a superconductor. Several properties of the material were observed, and nobody understood at that time why this is to be true. And BCS came out in 1950 or something of that sort with a theory for this. In a normal metal, the specific heat is proportional to the temperature. This is not any specific heat, this is electronic specific heat, and it is given by this expression. CV is partial of the mean energy by T, and we saw what is mean energy, right? We saw it is a partition function. The mean energy is given by this expression. Then the specific heat is how much does the mean energy of a particle change as you change the temperature. And this is just the electronic mean energy. We are not calculating the phonon mean energies, right? This is electronic contribution to the specific heat. If a material is a pure metal, it will have a linear transition with temperature. This I have not proved, but it should not be very difficult to prove. But for a superconductor, at T equal to Tc, the specific heat takes an discontinuous jump, right? So the resistance dropped discontinuously, the specific heat increases discontinuously. All these things tells you there is some sort of a second order phase transition because there is no latent heat. There is a second order phase transition. The specific heat jumps up, and from here it drops down even faster, right? So this discontinuous jump in specific heat is another signature of a superconductor. Another important property, or this is a consequence of all the things that we have studied here, is entropy. So here I'm measuring the entropy. I'm seeing that the temperature drops down. At T equal to Tc, the superconducting state has a lower entropy than the normal state. And obviously, the lower entropy indeed eventually comes out to say that the entropy will give you a lower total energy, right? So lower total energy, the system will prefer to go to be a superconductor rather than a normal material. That is the reason why at temperatures smaller than Tc, a material prefers to be in the superconducting state because it has a lower total energy, right? So this is the specific heat of the material. Superconductors exhibit what is called as an energy gap. Till now we have seen energy gaps in a semiconductor, right? It is also seen in other materials. It has to do with electron interactions with a periodic arrangement of atoms. But in a superconductor, it does not. The origin is not such. The origin here, I say it has to do with very strong electron-electron interactions. I will ask you to take it as I say. The proof I will try to show in the next lecture. But what happens is, let's say I have a material at 0 Kelvin, all the states below Fermi level are filled, right? In a superconductor, it will so happen that there exists a gap in the density of states surrounding the Fermi level. So all the states below and above the Fermi level has energy value delta. This is called as a superconducting order parameter. Below and above this delta are vacant. You have no states, no single particle states can stay in these energy levels. All the superconductivity is carried by electrons which are paired, which is called as Cooper pairs, which live at the Fermi level here. This is a very different and an interesting state which does not appear in single electron approximations that we have seen till now. This gap, which amounts to twice the delta, also varies with temperature. At 0 Kelvin, it has a energy of 2 delta, and as you increase the temperature from 0 to transition temperature, this delta reduces, right? So basically it comes down, and the way it comes down is reminiscent of the Hc that we saw previously, right, in the magnetization behavior. Meissner effect behavior. The critical magnetic field, that's what we saw, is the same way. The energy gap, the 2 delta, also drops down in the same fashion. Something called the Josephson effect is a very interesting thing which has multiple applications. It has applications in qubits that is being implemented by Google. We will soon see. Josephson made this bold claim in 1962. He said that if I have two superconducting materials separated by an oxide, something like this. It does not have to be an oxide. It can be a weak link, it can be an insulator, it can be anything. It can be a piece of wooden furniture as long as the dimensions are small. Okay, so I have two superconductors S1 and S2 separated by a very small weak link. Then I can still have a supercurrent from S1 to S2 such that it follows this relation. IS is a supercurrent, IC is a critical current through this junction, and del psi is the phase difference between the wave function in S1 and the wave function in S2. Obviously, we are already slowly going into the quantum mechanics. The wave function of an electron, as we know from quantum mechanics, is a complex value, right? Is some psi S1 e power I psi 1. Similarly, psi S2 is psi S2 e power I psi 2, and del psi is psi 1 minus psi 2. This is the phase difference between these two superconductors. The current is proportional to the phase difference. So if I impose a current through this superconductor junction separated by a very small insulator, I will enforce a change in the phase between these two superconducting blocks, and the current is just proportional to the phase. This is called as a DC Josephson effect. The AC Josephson effect is if I impose a potential on top of this. Remember, I am still in the superconducting state. If I impose a potential on top of this, then the potential will ensure that the phase will undergo random oscillations, right? So basically, d psi by dt, the change in voltage difference between the pads were enforced, then the phase will evolve such that d del psi, the change in del psi, is 2e by h cross into v. This means that if I have a potential v across these two pads, then the current will oscillate at a frequency given by 2e v by h cross, and the oscillating amplitude will be IC. If you solve this equation, you can clearly see, if you solve this equation and plug it into this, you will see that you will have a current which goes, this will be IC, this will be minus IC, and the frequency is 2e v by h cross. And you can notice that a potential of few microvolts will give you a terahertz oscillation. So a superconducting Josephson's junction is a very good terahertz source. Unfortunately, the power in this is so weak. So if you want to make a terahertz generator, you need to have a huge array of Josephson's junctions. People have tried about 10,000 arrays, which is not very hard to fabricate, by the way. People make millions of transistors in a small array. You can make millions of Josephson's junction in a small array. You will have a very strong terahertz source. But the problem now is to have all of them in phase. That's a problem for another day. So there are several applications, as we saw previously. First and the most easiest one is a very strong magnetic field, as we saw previously. That is because of the fact that the flux threading a loop should always be constant. So the flux which goes through this loop will be a constant value. Magnetic fields as high as 8 to 10 Tesla magnets, and now you have 50 Tesla magnets using superconductors. They are used in nuclear magnetic resonance, they are using magnetic resonance imaging, they are used in our CERN's particle collider. They are used everywhere. They are used in telescopes, they are used in hospitals, whatever, right? They are also used in sensitive photo detection. I will soon show how this is being used. They are used in astronomical imaging in what is called as MKIT mutual kinetic inductance detectors. This is developed by Jet Propulsion Lab in Caltech. They are used in single photon detection, which is used in quantum communications. You would have heard about secure communication, secure protocols, and such, which are already being implemented. ISRO recently demonstrated the first ever quantum communication in India. You require single photon detectors, which can be implemented using superconductors. Okay, so this is one such diagram which shows how to implement a single photon detector. You have single 64 photon detectors here. You have a single photon detector source. You can multiplex them, demultiplex them, play some games with this. I show this because this is something many of you would be interested in. A superconductor, particularly a Josephson junction, is used in a superconducting qubit. A superconducting qubit is just an LC oscillator. A Josephson junction, as I will show in the next slide, is an inductor. And if you can make a capacitor out of this, so basically this is a capacitor. They implement the capacitor in this fashion because you want a long capacitance. You have a large capacitance value, right? So basically this is a superconducting capacitor. You have an inductor here. So basically you have a tank circuit. A tank circuit is an harmonic oscillator. And a Josephson junction can be shown to not only be an inductor but also a nonlinear inductor. And when you have a nonlinear inductor, it is not easy to show, it's not very difficult to show that the energy levels are not constant energy levels as is true for any harmonic oscillator. And nonlinear inductance will ensure that the gap between energy levels are now different. You can tune the nonlinear inductance such that the gap between the first two states are small and the gap between the second and the third state is large. So what people typically do when you're implementing a superconducting qubit is that the ground state and the first state becomes very close and the second state is too far away, such that it does not interfere with our measurements. So when we have something like this, now this is very close to a two-state system, which we have been talking for till now, right? And now if I interface this with or when I interact this with electromagnetic radiation, I can make a superposed state of this 1 and 0 and 1, and now you have a qubit, right? You have a up spin, down spin kind of a behavior. And now if I incident this with an electromagnetic radiation, then I have a superposed state of upspin and downspin depending upon how this interaction happens. This is how a qubit is implemented, and this is how Google implements this. Microsoft implements this qubit in a different fashion by using what is called as a Majorana fermion. We will not go there for now, but Google has successfully implemented, I think, 50 such qubits and probably trying to interface even more now. We will stop our initial discussions on superconductors with just this very simple demonstration to show that the Josephson's junction that we have been talking till now makes a nonlinear inductor. These are the two equations as we saw previously. One is the DC Josephson's junction, DC Josephson's equation, which is IS, the supercurrent, is IC, the critical current, sine times del psi. Del psi was the difference in the phase value between the two pads as we saw previously. And d del psi by dt is 2 pi into 2 ev by h cross. This 2 pi is added because of the unit mismatch that we had previously. 2e by h cross is inverse of the magnetic quantum flux as we saw previously. So this equation can be written as d del psi by dt is 2 pi by psi into v, right? So I take the first equation, I differentiate it. Dis by dt is ic, sine del psi will give me cos del psi, and d del psi by dt is the second equation, is 2 pi by psi naught magnetic flux quantum into v. And this equation is something which we know, right? Di by dt into L is V, and Lj, I write as Lj is an inductance of the Josephson's junction, is psi naught by 2 pi IC cos del psi, right? So psi naught is a constant, 2 pi is a constant, IC is a constant. Only thing now which varies is a cos of del psi, and cos of del psi makes this inductance a nonlinear inductance. It's easy to see. If del psi turns out closer to pi by 2, Lj explodes. So you have an exploding inductance when you set the del psi. So if you can initialize a qubit, that's what they call as initializing a qubit. You initialize a qubit by putting the phase difference between the pairs in the Josephson's junction such that the inductance is maintained to keep the second excited state far away from the first and the ground state, such that now when you interface it with the electromagnetic radiation, typically in the microwave region, you mix or make a superposed state of first and the ground state, and you form the qubit, right? So with this I will stop the lecture on the introduction to the superconductors. In the next lecture we will go with phenomenological models shown by the London brothers, and probably if time permits we'll use the Ginzburg-Landau formalism. We will end with the BCS idea, and whoever is interested will go even further. I can explain how the BCS theory works. You need to have a little bit of quantum field theory, but that's fine. We can actually handle it. All right. So thank you.